Yes, we're recording. Okay. Uh, Welcome to the first video of a video series. And the purpose of this video series is actually it is just my learning journey. And I thought it would be nice to share this learning journey. Right now, I'm just giving just an introduction to the series. This is not something that will be in all the videos. This is just the introduction to the series, why the series exists, what am I trying to do here. So my name is Amit, and I studied wireless communication uh, in my masters, and I work in the wireless communication industry. And very recently, which year is it? 2024. Yeah, I came across this modulation, a novel modulation technique meeting 5G high mobility and massive MIMO challenges. So this guy, Ronnie Hadani, and the other people. So these guys have come up with this new modulation technique, and what they propose is that it works very well in scenarios of high mobility. Because right now, I'm I'm sure that everybody must have experienced that when you are on train, you don't get very good reception, right? Cellular reception, LTE or 5G, it would not be that good because even when like say you're driving on a very fast highway, so speed limits are like 90, 100, 100 plus. So your data is the data speed that you get right now is not that good. The wireless communication system is not designed for very high mobility. It doesn't work well. So what these guys saying is that this OTFS is something that solves the problem. So I mean this, I think they introduced this in the year 2017. So I am only uh, coming across it now this year while I was doing some other study. And in this paper, so I have not read this whole paper, just some parts of it. Mostly I have watched YouTube videos because this guy Ronnie Hadani, he has given a lot of YouTube videos also. There are other like university professors who have explained his concept of OTFS on YouTube. So there are many resources from where we can learn this. But I couldn't understand what this OTFS is from all of those resources. The fundamentals must be shaky because of which I'm not able to understand. New domain that they have proposed. So what they, as you can see here, that they talk about delay Doppler domain instead of the time frequency domain, in which like the the best modulation technique, which is this OFDM, uses that time frequency domain, and they say there is a new domain which is a delay Doppler domain. The axes are like delay axis and Doppler axis, orthogonal axis. They say if we do our modulation in this domain, it can combat the linear time variant channel. I mean, it can make that also invariant. Uh, yeah. So, so OTFS modulation, I couldn't understand it from the paper or from the videos. So what I thought was to let's go again, revise some of the concepts that are important, which are also involved in OTFS, things like FFT, inverse FFT. One of the things that they use are like two-dimensional FFT. So FFT not on a signal, which is a function of time, but a signal which is function of time and frequency. So basically, yeah, two-dimensional signal, and on top of that, they perform FFT and they take it to a different domain. And yeah, yeah. But I mean, mathematically, you can try and see their equations and you can make some sense. But that intuitive understanding of like how it works on high speed systems, how it works well, how it beats OFDM, that intuitive understanding is something that I wanted to develop. So I thought of going through all the concepts again, and I just thought why to just do it alone, and not alone. Like I'm doing it, I should share it as well because I'm not sharing. I'm not trying to teach here mostly. What because I'll not be going into some very complex mathematics or yeah, all that sort. What I'll be so in the background I'll be doing my study, but in this videos what I intend to do is just all the concepts that I'm reading, all the important concepts, the significant ones. Just, just talk about the intuitive understanding of those concepts. How intuitively can we understand them? Because intuitiveness, once you develop that, then it is. Yeah, I mean, I find it much easier. I find myself much more comfortable with any concepts once I have some intuitive understanding. Too much, the word intuitive has been used. Okay, so let me write the title. So I have prepared this text file also and all the settings so that it works well. So the title of the video is Developing an Intuitive Understanding of Digital Understanding of Modern Modern Digital Wireless Communication Systems. So this is the title. Okay, and this is the first video in this series. I don't know how long this video is going to be, but it should be within an hour or maybe within 30 minutes. I don't have a lot. Okay, so what is the first thing that I want to discuss? Today's video, right? Because I can say number one. What is the number one thing? Number one thing, the important concept which I think is is very like it's very important part of the modern wireless communication system, and is one of the very fundamental concepts. So which is what are IQ? What are IQ values? I mean, there could be a lot of questions actually, uh, but what are the values or like IQ samples or IQ plane? You can say a lot of things about it, but I want to focus on what is this IQ, right? IQ basically, I stands for in phase. Maybe make it better. In phase, the Q stands for quadrature. Wow, quadrature phase. In phase, quadrature phase. Yeah, yeah. So in this, I'll be just covering what is this IQ, but not like very mathematical, but intuitively. Okay. So what about IQ? Why is IQ important? Why is IQ present in our wireless communication systems? So to explain what IQ is, let me first like set the stage for introducing IQ values. So for that, what I'll do is, mm, hmm, so let's consider some of the very popular modulation schemes. It's fine. AM. So how does an AM signal look? So since it is amplitude modulation, since it time, so amplitude modulation is some high frequency carrier which is modulated. Yeah. So some signal. So basically, you're changing the amplitude of the carrier, and in this envelope, you have the information that you have sent. This envelope contains the information. So for AM, there will be some decoder which can help you get this uh, envelope. Usually would be a low pass filter because there are a lot of components in this signal. Things like the carrier frequency component and then some lower uh, lower frequency component, which would be the data, which is the rate at which this envelope is changing. But anyways, there would be some type of decoder for amplitude modulation. Then let's look at what is the other popular modulation scheme, which is FM. So how the FM waveforms look? So they follow they don't change the amplitude of the carrier. So they would usually look like mm, something like this. Like the frequency will keep changing, frequency modulation, and in the change in the frequency is the information that you're transmitting. And then there are what? So these were like the mostly used for analog communication. And now, but you even the digital communication you can do FM and AM also. Okay, the next popular scheme would be what? One of the NPSK, I would say NPSK. PSK is phase shift keying, and N is the number of phases. So the number of phases means how many symbols you're transmitting. So if you're transmitting just two symbols, it will be binary PSK, BPSK. If you're transmitting four symbols, it will be quadrature, QPSK. But that means the N represents how many symbols you how many different symbols you can transmit using the scheme. So for let's say I'm taking the case of N equals 2. So what will happen is, let's say I'm drawing some sine wave. Let's say this is the time period of what one I should complete 2 cycles. Okay. So this is the time period of one symbol. Then I want to transmit the other symbol. So let's say since it is two symbols only, the two symbols can be 0 and 1. So here I'm transmitting 0. And let's say when I want to transmit 1, I would phase shift by 180. So 0 and 180 are the two phases that I. So when I phase shift it by 180, it will the same carrier, the same sine wave will be shifted upside down. It will become like this. So let me draw up to the next cycle, and I should complete 2 cycles. One, two. Is it right? So here, correct. So I mean, it is not very properly drawn, but you get the idea. So think like it will keep on going, and uh, so there will be some decoder for this to detect the change in the phase. So, so these different, and then there is another scheme. I should point that out. Don't have space. I can scroll down always. The other scheme is NQAM, where N also represents number of symbols that you want to transmit, and QAM is quadrature amplitude modulation. Basically, what this modulation scheme is that you can change the phase, and the amplitude. That means, like for example, this NPSK scheme, you can only change phase. So the phase change contains the information. So in QAM scheme, the phase change and the amplitude change both can contain the information. So what a typical signal would look like. So it can carry more information because you can create more symbols. Okay, so some example of the QAM I can give. I'm starting from here because there's not much space. We can start also here. So let's say 2 cycles of sine. So this is one. The other is no phase change, just the amplitude change. So let's say we draw these boundaries first. It's a phase change and amplitude stays the same. And let's say another phase change, but yeah, so things like that can be QAM. So so what I'm trying to get to is, so there are different kinds of modulation scheme using which you can modulate your carrier to carry the information. Now, before the idea of IQ samples, the demodulator for like this scheme, AM, the demodulator for FM, demodulator for PSK, they were all different hardware. For example, you cannot have, like for example, FM if you take. To generate it, you need some voltage controlled oscillator, right? You need some VCO. So this block, something that if you change the voltage, it will change its oscillating frequency and some for modulation, and for demodulation you must have something which can sense the change in frequency and then convert it into voltage. So and that technique would not work for this AM, right? Because AM is just filtering and then getting the data. Similarly for PSK, it will be different style. You need to change phase. So basically, for all these schemes, the hardware is different. People came up with a technique so that the hardware the hardware part never has to change. You can minimize what you do in the hardware, which stays the same, and then some signal processing you can do in software and to make it more sophisticated as in it can do more things. People came up with a hardware design along with a software component which can do all these modulation scheme on the same hardware, and you just have to change your software to modulate or demodulate them. And that technique is what uses this IQ. So let me now introduce how this IQ samples or this IQ values or this modulation technique can help you do any kind of modulation. All sorts of modulation you can do on this. So let me write down what IQ, where the IQ comes from. What does it mean? So this again, I'm writing this mathematical expression. This is y of t, and writing q here, cos 2 pi f c t. C is for the carrier frequency plus I sine of 2 pi f c t. So in this equation, q is the coefficient for this cos component, I for this sine component. So basically, I and q are the coefficients of this equation. And by changing q, I and q values, you can create any modulation scheme. And this gave rise to the idea of software defined radio. So software defined radio is in SDR, just software defined radio. Now, what the concept of software defined radio is that basically you just need two components, and with these two components you can get a system which is very sophisticated, very uh, scalable, can do lots of things on the same system. You don't have to change your hardware. And the claim of the system is that you never have to change this radio part. So this part stays fixed, no change here, and which is the real hardware. So the hardware is fixed. That's the real advantage. And then software is what you can change with, and you can change the software in such a way that it can help you, you know, modulate or demodulate all these different schemes with just one piece of hardware. Now, okay, let me draw a very simplistic diagram of this radio. SDR hardware. Well, by the way, I think maybe I can show some of the popular hardware. Hack RF, Hack RF1, I guess, yes. Hack RF1 on a PCB grid card, okay, is a wideband software defined radio. Basically, by wideband, what they mean is that the carrier frequency, it can go from I think it can go from few megahertz. I think they have shown here. Yes, 1 megahertz to 6 gigahertz. It's a very wide range of carrier frequency. So basically, if your carrier, if you want to decode or if you want to demodulate something, or you want to modulate and transmit something, and your carrier frequency falls in this range, you can use this hardware. And it does not matter what scheme you're using, AM, FM, QAM, PSK, it will be able to do all of that. Uh, but they're not given much info on that. I got a one website. Yeah, this is how it looks. I think this port goes must be the antenna site for reception and transmission, and these two are the TX chain, RX chain, and yeah. So 1 megahertz to 6 megahertz, half duplex transceiver. Half duplex as in it can do both transmission and reception, but only one at a time. So 20 million samples per second, we'll cover this. 8-bit quadrature samples, 8-bit I and 8-bit Q. See this I and Q. We'll see what this IQ mean here. Compatible with GNU radio, yes, I know that because they have this hack RF support. Blah 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 blah. A lot of things. So I think this is costly. I have checked on Amazon. It costs around 40,000 rupees. I think. Yeah, 40,000. It's very costly. I wanted to buy it, but don't have money for these hobbies. What is the other? Pluto. Pluto SDR analog devices. Yes. Board is there. Adam a- add ADALM Pluto. Yeah, so this is how it looks. These are the antennas, and then this is the USB connection. I think USB connection to like your PC where the software is. So this is just the hardware part. Okay. Have they mentioned IQ here? No. Flexible rate, 12-bit ADC, DAC. Yeah, okay. What am I trying to show here? I think nothing, just a diagram. You can see this diagram also. Yes. Yes, I think I will be creating this diagram only, but a little better. Something that makes sense. Okay. So we'll keep this diagram as our reference. This is the generic diagram for all the SDR hardware. Let me draw. Okay, so what they're trying to say is, as I showed in this equation, right? Q cos 2 pi fct I is 2 pi fct. So first, the premise, the claim here is that just varying I and Q, you'll be able to modulate, demodulate all of those schemes, right? So now what we will try to see is how can this, how is this true? How and how do they do it? Okay. Uh, so so right now I'm just implementing this equation in the hardware. So the idea of SDR. So as I said, it comes from this equation y of t equals q cos 2 pi fc t plus I of I times sine of 2 pi fc t. Now let's uh, make that hardware software component. So I'll just draw the hardware which stays the same for any modulation scheme. So for example, I think I'll do RX, I'll do reception. So yes, as I showed earlier, this is the Pluto SDR from analog devices, and this is another SDR from HackRF. And I also should like this 8-bit INQ values it outputs. Yep. Okay. So this has much like some details, so I'll follow this one. So the one which has PA is for it works. This chain works for TX because in the end you have a power amplifier for TX, and this is LNA is low noise amplifier. This is for RX. You want to amplify the incoming signal because it is very weak, and you don't want to amplify the noise, only the signal part. So it is low noise amplifier as much as possible. Okay, so we'll follow this chain for RX. Okay, so let's say I have, for simplicity, let's say I have two chains. Two chains. Both of them are receiving the same signal, right? Signal comes to both of them. So the first thing is, according to the diagram, is LNA, right? So first thing I'll do is I'll do a low noise amplifier thing. Yep. After the signal has been amplified and noise has been suppressed as much as possible, what I want to do is whatever is coming, I'm assuming this Y is that is coming because I can represent any signal with this form. So let's say this is Y, right? AM, FM, PSK, QAM, anything is can be made out of this equation. So let's say some form of this equation is only coming with some noise and some weird INQ values. So I make them go through a multiplier, right? I want to multiply. I want to multiply what? My carrier frequency, cos of that, uh, I mean the 90-degree phase shifted of my carrier with the Q. So what I do is here is my local oscillator, LO, and it is one of the arguments to the multiplier. This is the other argument, which is Y of t here. Both of them are getting Y of t on this. Let's write it here. Okay, should have made it dotted. Anyways, so this is with phase 0 degrees, and here it is with 90 degrees phase. Basically, then it makes it sine wave, and this makes it cos wave. Now these were the inputs to the multiplier. What I'll get in the output, as you already know, if for y of t, if I multiply cos, it will become like cos square and sine into cos. This part I'll be able to cancel out in my filter, sine and cos multiplication because they are orthogonal, so they cancel each other's component. And so basically, when I multiply y with cos, I can extract the q component and I can completely suppress the I component. So what happens is if I multiply with I sine here, I'll get something which is proportional to I and has no component of Q. So I got I uh, and I got Q. But these I and Q are, still some analog time varying values, but I got the correct I and Q. Then what I do is I make them go through LPF, low pass filter. This is what this is, to remove noise and make sure that the values of I and Q are, remove any frequency components which are not desired. So make sure that it is in the right LPF. After I have taken them through the LPF, low pass filter, what I do is I sample them. Right? I want to sample them. I want to make them discrete values. And this sampling is done at some frequency. Let's say Fs, my sampling frequency. So LO is the basically your carrier. So you multiply like your carrier with your signal so that you can remove the carrier. So basically removing the carrier means your data was on a very high signal, right? YT is very high frequency signal. You take that high frequency signal and then you translate it to very high frequency signal. We usually call it as passband. So I can say that this region is passband, right? So here my data is passband data. The data is still on very high carrier. Then after this multiplication happens, these mixers are called multipliers, mixers, same thing. After multiplying, I can cancel out my carrier components and I can only get the baseband component. Baseband component means I don't have any carrier, it is just pure information. So it's here on onwards, it's the baseband. Okay, so I got I, Q in baseband, and then I make them go through low pass filter, remove unnecessary frequencies. And then I sample them at a rate. And you must know already that if you have some signal, and which is your data signal, let's say, and it has the highest frequency it has is, let's say, some f naught. To be able to recreate the signal using samples um, accurately, you need to at least sample your data at frequency which is at least double or more than double of the highest frequency of a signal, which was f naught in from our discussion. So this fs sampling frequency is mostly like double or triple or like more than that times of, more than two times of your data signal, or more than two times the bandwidth of your data signal. So that is how I'm sampling it. So basically, let's say for Wi-Fi cases, right? You have a 20 megahertz band, and the 20 megahertz band of a Wi-Fi is at 2.4 gigahertz frequency. So this must be 2.4 gigahertz then, and this would be 20 megahertz then. Okay, so the sampling has done. So now I got some samples, but those samples could be some any like float value, like they can be any analog value, right? So what I need to do is I need to take those values, convert them from analog to digital. By digital, I mean taking those values and making them like it can vary from design to design, but I will convert them into 8 bits, let's say. I in 8 bits and Q in 8 bits, and then later on I do a special kind of addition so that the output is now 16 bits, right? So each symbol is a mix of I and Q. So it's a 16-bit data. Now, what I will say is that this 16-bit data contains what? Basically, it contains I and Q values, and this is a baseband signal. It's not very high frequency, and it can be like there are the software can work on the 16-bit data and can extract whichever modulation scheme YT had. So it will be able to demodulate in that scheme. So from here on onwards, the software will be able to take care. So this block that we have just drawn is your SDR hardware, and the claim is that you don't have to change it. Once you have this hardware, does not matter if YT is AM, FM, OFDM, QPS. no, I mean OFDM is a baseband processing technique, but any of those modulation schemes, you can modulate them, demodulate them using this hardware. The hardware does not have to change. Let's see if I drew it correctly. So first is LNA, low noise amplifier. Then I have a mixer, there's a mixer. Then I have a filter, so low pass filter here. After that I have ADC, but actually it is like samples and then ADC. Then I have again some filter, which I didn't draw, and then some FIR, which is frequency impulse response. No, no, it was what? I forgot FIR. Some digital filters. This finite impulse response. I forgot. Okay, this part. Yeah, but you get the idea. 16 bits, and then anybody can, any software you can use to process on it to convert this into the information, the true information out of this. Now, okay, I have some other. There's this very nice website. Yeah, this silkendsp.com. It is amazing resource for learning OFDM concepts. It's very good. I find it very interesting, very nice, very good amount of detail they have covered. So just to cross check our diagram here, what I'm showing is that this is the receiver part. So this is what I have done here. So you see in the receiver, you have this local oscillator, phase shifted by 90 degrees, passed on both multipliers. This is what we are doing here. Then after this, we get I and Q passed through low pass filter, sampled, and then ADC. Low pass filter, sampled, and ADC. Then serial to parallel, that is all different thing. Then you do FFT based on if you want to do OFDM or not. This is like OFDM specific, so they're doing it. Uh, but yes, so the concept of SDR is that if you have this, you can do all other things with this. Now, this is still just talk, right? I have prepared a GNU radio flow graph to show if this equation if and varying I and Q can really give you all those modulation schemes. So I think some of the modulation scheme must be very obvious. For example, AM. To do AM, you can just keep any of them zero. Let's say you keep Q as zero and I component. Then you can vary I component, and that means basically you are doing an amplitude modulation, right? For PSK, I think the trickier one is FM. How do you do frequency modulation? So basically, uh, yeah, let me, I think, show you first the diagram. Okay. So this is the flow graph that I made. It looks like there is a lot going on, but actually most of the blocks are just displaying the waveform. The actual thing is not that complex. So let me explain. So first is the sine wave, the cosine wave. Two. This is the carrier, and this is the carrier phase shifted by 90. I couldn't do that 90-degree phase shift from this carrier because it was not somehow working with other blocks because it needs some complex inputs. But I made the whole thing work with I wanted to make the whole thing work with the float values only. Yeah, so I had to make the sine wave, cos wave with 256 hertz frequency, and then I take them through a multiplier as but okay, so I'm actually, this is the reception one. Yeah, and I have drawn for transmission, but you can see basically, as you saw here also, transmit chain and receive chain are kind of similar. So like filter, mixer, ADC, DAC, their counterparts. So how the transmission should happen is that you have your I and Q, which get multiplied with your sine and cos component. So here is the sine component going into this multiplier block, and you'll see that the other input to this block, which is this blue line, is the I component, and this I component comes from these sources. These are some signals. I'll show you in the diagram how I control these signals to make sure all kinds of modulations are possible. But I'm only changing these I and Q values. Then similarly here, the cos goes into this multiplier block, one of the arguments, the other argument is the q component. And the q component is also exactly same. I'm changing I in, I'm generating I and q from different sources, and I control them from the simulation. And here these blocks are just to display the constellation diagram of using I and q, because the I and q, I think I didn't explain. The concept of IQ, since like here also you see that I is like in phase, quadrature phase. So basically you can make a I and Q plane because they are orthogonal to each other. And in this plane, if I put this point, every point is a sinusoid with some amplitude and some carrier frequency. So here this is at some 45 degrees phase shift, and this is some amplitude. If you take the like this length, it is the amplitude. And if similarly, if you change it to some other position, it will have the same frequency, but it will have a different amplitude and a different phase. So like that, you can control the phase of the the carrier. Every point is a carrier with different amplitude and phase. So let me show that wire diagram. So this is my carrier getting multiplied with I and Q, and after multiplying, I add them together here, and then this is my output. And those output I'm displaying in different types of graphs. So this is a time sink, this is a frequency sink, and this is another time sink. Okay, so let's run it and see what do we have. Ah, nice. So okay, so let's just focus on this carriers. uh, Name of this misleading kind of. Let me suppress this thing. Okay, now we see sine carrier and cos carrier, right? You can see it starts from 0. So sine wave, the frequency is 256 as I showed in this one. Yeah, frequency is 256. You'll see 256, 256. 256 hertz is the frequency. And let me increase the number of F50 points so that it is more accurate. And zooming in. Yeah, I think I should zoom in more. Okay, so if you see, it is zero point 0.2, zero point 0.4, somewhere around zero point 0.3. It is not zero point 0.3, it is at 256. So basically, it is displaying it correctly that I am in 256 hertz frequency component. And it's just negative part, so we only just focusing on the real part. So that means we have only one carrier, one frequency that is going on. Now this green signal 3, is what? Is me just simply adding cos and sine. That means when this I and q value, if I keep I and q both as 1, I'm basically adding cos and sine. And when both the values are 1, which is shown by this q and I component, I have kept both the values at 1. So you'll see it is some sinusoid with the same frequency as the carrier. So the frequency has not changed at all, but there is a different phase, right? And if you see, you can change the phase of the carrier by changing the NQ values. So I'll show you gradually changing the Q value first here, and then you'll be able to see how the graph, the green curve, does not change in like frequency, but it shifts in time. That means there is a phase shift in the uh, signal. There is the addition of the carriers. So once you control any INQ value, you will be able to phase shift the carrier. So you'll see if I change this value, you'll see the phase shift. You see it is moving in time. There's some in effect on the amplitude also, but that's not important right now. What I'm trying to show is that you can control the phase. So 1 is with like 45-degree phase shift from the sine wave, and -1, let's take values. It's like a 180-degree phase shift now I have done with sine wave. Whatever I had originally, I'm exactly phase shifting that green signal. So that means you'll see the green signal at -1, and +1 is complete inverse of itself. So +1 if I do, yes. I mean, it's not that obvious, but yeah, you'll be able to follow it. So That means what we're able to see is that, yeah, controlling I and Q, I'll be able to control the phase. The frequency doesn't change at all. You can see from the diagram also this frequency spectrum also you'll be able to see that the frequencies do not change. See, I keep on changing the frequency stays the same. Okay, nice. So I'm able to do what? PSK. And AM, so is very obvious. Just make one signal zero. Yep. And then keep changing this value. And now you're amplitude modulating the carrier. See? Okay. Now let's see the interesting one, which is frequency modulation. How would you do frequency modulation using this equation? Uh, this equation cos to pi ct. By bearing this q and I, how will you change the frequency of the carrier? Now, focus, this green line is the output signal, which is like the carrier which is modulated. And here, that green line and this red line are the same. It is just red here. And oh, this is wrong. Yes, because the red line is the modulated signal. It's a carrier with the information. It is not the pure carrier. So yeah, this is wrong. It is not modulator. It is the modulated. So it is interchanged. Okay. Anyways, now to change the carrier frequency, what you can do is if we keep changing the phase continuously, right? Not like discrete, like making it 1 1 or then 1 0 -1 -1. These are like discrete values. So they'll give you like a discrete phase shifts in the carrier. But if you continuously keep changing the carrier, that changes the frequency because I'll show you how the frequency it will change. Or maybe I can try to draw a diagram. Mm, 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 where is the here? Okay, let me open a new one. So what I'm trying to go for is, let's say this was your carrier. Very bad actually. And let's say this is the time period. So if you change the phase continuously, so what you're making it happen is that you can drop it down fast because you're changing the carrier phase, right? So what I want to say is that this is the time period, and this is the next time period, and then after this is the next time period. So there is this gap, right? Wait a minute, right? This is wrong, no? Right? This is the, and for here this is the house. See, so basically, if you see, I if I draw a high frequency signal, it basically means is that the phase here, that means the delay in time is continuously changing. So here it was something, a smaller value, and then it is now greater value. And if I keep going ahead, it will be even greater value, and then it will change, right? So that means if I can interpret a higher frequency signal, so if I just change the frequency to a higher frequency, I can interpret it as change in phase, but it is a continuous change in phase. But maybe this I couldn't do justice with this explanation, but I can explain it via this flow graph. Okay, so to be able to do that, what I'll do is I'll make this I and Q go in, keep moving continuously, right? If I keep making it move continuously, it will change the frequency of the signal. Even if I make it move at a fixed rate, it will change the keep changing the frequency of the signal. Okay, let's try to demonstrate. So first, let me disable the QPSK. By disabling the QPSK, I mean I and Q values will be zero. It doesn't show here, but you'll see that the green, which is the modulated signal here, is, and the red one here are zero. Now let me enable the frequency modulation. Okay, As you see that now the green signal, you can see, is of a different frequency now, right? It does not follow the same frequency. And to make the effects more dramatic, no, I don't want to increase my carrier frequency. Let's keep the, no, I can increase the carrier also maybe. So I've made the carrier around 4.4. That means 400 hertz. I've made it now. And let me modulate my. Oh, I think I should. Yeah. Let me modulate. Okay. What this payload means is it is this 96 is the frequency of the INQ. So INQ are just some sinusoid. So my sinusoid is my, you know, the sinusoid is my data signal now with very low frequency compared to the carrier. And because of that sinusoid, I'm able to continuously make it like 0 to 1. It is continuously changing. So because of that, you'll see that there are two components now showing up. That means there's one lower frequency and then one higher frequency, right? And these two frequency components came because now my whatever I'm transmitting has multiple frequencies in it, and multiple frequencies, why? Because of this rotation. I mean, it is not very easy to see. Let me see if I can make it stop at a place where it is obvious that the frequency. Mm, huh. So here you see that the red signal is the signal which is modulated one, right? So you see that based on this blue line, the rate at which the signal change, the frequency of the signal will keep changing. And you can see here that this is very high frequency part where the change from this place to this, whoa, the change is very much visible. But here you see that, okay, there's some memory issue. Okay, let me stop. With just changing your IQ values, which can be controlled by the software or when you're transmitting, or can be manipulated by the software when you receive it. On the air, you can actually send carrier with the different frequencies. Different frequencies, and you can see here that between these two peaks, the, the timing is different between these two. Between the peak, it's different, and you can consider this as a peak, but the rate of change from here to here is, yeah. I mean, I wouldn't encourage that. You see, I mean, there is one. It is kind of wrong. It's approximately correct that you can see the frequencies by just eyeballing the waveform. That okay, yeah, the rate of change is obvious. That there's different rates. So like here, the rate of change is fast. The signal goes from high to low very quickly. But here in this range, there doesn't change that quickly, right? Rate of change is slow here. Rate of change is very fast here. But if you go by that, why I'm saying that this could be wrong is, let's say you have a normal carrier, right? This is the carrier and this is the frequency spectrum of that carrier. According to this uh, frequency spectrum, there, maybe you're not able to see this. Let me show from here, maybe first half. Yes, so these are the FFT size. So if I control the FFT size, the output will be much more accurate. How many FFT points I need to display my graph. Okay. This is not. So what I'm trying to show here is that this is 256 hertz, like nothing has changed, and it is peaking at that. That means it's just trying to say that there is only one frequency, because if I keep increasing my 50 size, it will become like an impulse at that point. And you see this, whatever this noise is, this is almost nothing, because from this curve you see it is minus 50. You see, and if you understand dB, minus 10, uh, minus 10 means the value has reduced 10 times, right? Minus 20 means the value has reduced 100 times, right? And minus 30 means the value has reduced like 1,000 times. So 50 is basically close to a million times reduction. So this value is even below my 150. So it is nothing. So these values are nothing. So there is no frequency here, right? So it just shows that this is just a sinusoid with only 256 hertz and nothing else, right? But that you will cannot interpret by looking at the waveform and by the concept of rate of change of signal, right? Because rate of change is what you can know the rate of change by the derivative also. So derivative of sine would be your cosine, and we all know, like if I press this, you see, uh, yeah. So when the other, basically, when sine is at its peak, the rate of change is zero, right? This is the maximum rate of change here, this region. Things are changing at the maximum rate, and this is where the rate of change becomes zero, and then it goes in the other direction. So it should show that there are like a zero rate of change also, right? Zero component should also be there, but it's not there because this wave that we're seeing, the rate of change is the correct interpretation. That frequency is actually rate of change of the signal, but this sign is a projection of a rotating vector. And when it is actually going here, it is not going here and then coming down. It's basically, if I try to show in a diagram, like what I'm trying to say is that it looks like as if, okay, the carrier goes here, slows down, then comes here, then changes the direction. And to change the direction, you have to, the rate of change has to go zero somewhere. But this is not what is actually happening. If we tilt this axis a little bit, we just rotate it, and we can see a different color. Let's say this plane. So I've rotated this thing, and now signals comes out of like that. What is actually happening is that we are seeing from this is our eye. We are seeing from here, and the circulating vector goes like this, but it keeps moving forward, right? Since it keeps moving forward, we just see its projection, and the projection as in on this surface, we see the projection. And on this surface, what we see is that the signal is going like this. This is what we see, that has peaked here. But if you see from this circular motion, it is actually rotating at the same rate. It's not changing its direction. It is rotating at the same rate. So this is what I'm trying to show. So you cannot really, like, I mean, that concept is not completely true. It's kind of true because it is a projection. And that is why we had negative frequencies, because this Fourier transform is actually working on the rotation of those uh, rotating phase. And yes, just to clarify, this plane that we that I mentioned here, this is not IQ plane. IQ is different. IQ is a cos and sine component, and this is real number and imaginary number. So these are actually this is same as I think I'm getting it wrong, but some, this is like cos theta can be represented as like half of e raised to plus I theta. I don't know, minus. Wait, let me just see it right. Uh, 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 where, hmm, where are you? Come on, come on, come on, come on, come on, come on. Oh, man. See here. Half of e raised to ix plus half of e raised to minus ix by 2. That means this half. Yes. So what it's trying to say is that minus j minus I theta, I guess, right? Cos x ix. Yes. So this half power and this phasor means rotating in one direction. This one is rotating in another direction. And then you add them together and then you get that cos theta. So this cos theta actually contains both the information, and this is not cos theta completely. This is just a projection of it. Yes. Yeah. And there's much deeper conversation can be had on that. But yeah, so the Fourier transform understands that part and doesn't just go by the rate of change of this projection. Okay, so yeah, these were the things I wanted to cover. What else? Yeah, so in the upcoming video series, my goal is to what things I'll revise, like I study and maybe share here. The next thing I want to do is what was that? Understanding OFDM. Basically, why OFDM, right? Why OFDM? Why we had to move to OFDM? Why it is the best modulation scheme that we have today? Why it is that? And then there's a sub part of it which is why FFT or IFFT for modulation. Not completely this is modulation. FFT, why FFT IFFT as a part of modulation, right? Why do we have to use FFT or IFFT during the modulation, right? Because we're doing just QAM, as I mentioned earlier, right? This OFDM, we mostly like if you take all these modern wireless communication protocols of like Wi-Fi, LTE, NR, 4G and 5G, that is, they basically use PSK and QAMs. But both, all of them, they use FFT, IFFT. So what is the use of IFFT, FFT in this process of modulation and demodulation, right? Yeah, so these questions I will try to discuss in the next one. Yeah, thanks for watching. Bye bye.